Hi there, this is Thermal Physics Lesson 8, and this one is Kinetic Theory and Average Molecular Kinetic Energy. So just a bit of basic information to start with. The kinetic theory of gases. So the kinetic theory of gases states that a gas consists of point molecules and that they move about in a random motion. If you want to pause and take some notes, please feel free to do so. Let's move on. The kinetic theory explanation of how gas pressure changes with volume and temperature. So first of all, with volume. So let's imagine if the volume of a container is decreased, there would be a greater number of molecules hitting the inside of the container per second. Therefore, it's obvious that a greater force would be exerted and pressure would increase. So what about temperature? If the temperature of a container is increased, the molecules, they will move at greater speeds as they would gain more kinetic energy. Therefore, more molecules will be hitting the inside of the container per second, and they will each exert, individually and collectively, a greater force on the inside of the container. A greater overall force will be exerted, therefore the pressure would increase. If you want to write any of that down, please pause to make some notes. Let's move on. Molecular speed variation. So the molecules inside an ideal gas have a continuous spread of speeds, as shown in this graph. So not all of the molecules within a gas travel at the same speed. The majority will reside on average, as shown in this graph. And then we have outliers. We have slow-moving molecules and faster-moving molecules. So the speed of an individual molecule may change when it collides with another gas molecule, but the overall distribution of the speeds remains the same, provided that the gas temperature does not change. The only thing that dictates the speed at which the molecules will move is the temperature of the system itself. So let's see the effect of temperature change. So as you can see, a higher temperature gas shifts the graph downwards and to the right. So more molecules at the extreme ends will be travelling with higher speeds. The average has reduced in the number of molecules and shifted to the right. And there are less molecules travelling with really low speeds on the left-hand side. Remember to pause at any point if you wish to make any notes or draw the graphs. So what about RMS molecular speed? What's this then? Didn't mean to do that. So if a gas contains n molecules, each having speeds, C1, C2, C3, they're just the different speeds of each individual molecule, then the root mean square speed is given by this. It's just the average, so you would add all of the speeds together and then do an average as you would normally. So why is it root mean square? So CRMS. Well, what it means is that you square the values. We actually work backwards from the right. So we square the values, then take an average, and then square root the answer. Now, the reason that we square each value is because we have to select a direction to be positive, which means that there will always be negative values. And obviously we can't take, if we have an equal distribution of particles, say, moving to the right and moving to the left, we're going to end up with an average speed, if we just use the positives and negatives, of 0. So we obviously need to compensate for that. So here's an example. It says calculate the RMS speed of 4 molecules having speeds minus 300, 340, minus 350, and 380. So what you could do is you could do the RMS, you could square each value, then take an average, then square root. So obviously minus 300 squared would be 300 squared. So we could do 300 squared plus 340 squared plus, remember the negatives when you square them just turn into positives, plus 350 squared plus 380 squared. and then divide by the number, so there's 4 values, and then square root. You could really, in reality, just ignore the negatives and just use the magnitude and just do 300 plus 340 plus 350 plus 380 and then just divide by 4 to get an average. You would get the exact same answer. But just be mindful of this. In an exam, if it asks for an RMS speed from a selection of values, I would advise to show this correct technique, the RMS. So just bear that in mind, please. The answer to this, by the way, in case you wanted to do it, is 342.5 meters per second. So let's move on. The kinetic theory equation. So for an ideal gas containing n identical molecules, each of mass m in a container of volume v, the pressure P of the gas is given by PV equals a third nm CRMS squared. Now this can also be written as I do if I'm writing on paper or on a screen. PV equals a third nm C bar squared. C bar squared just means average, and it's essentially the same as writing CRMS. I use this one exclusively, really. I don't ever write this. So PV equals a third nm C bar squared. Now this information is really important above. So n is the number of identical molecules, each of mass m. So m is the individual mass of each molecule. So let's move on. Here's a question if you want to pause and have a go. And then I'll take you through the answer. So a container of volume 0.05 meters cubed has 0.4 kilograms of an ideal gas at a pressure of 2 times 10 to the 7 pascals. Calculate the RMS speed of the gas molecules. So what we've got is PV equals a third nm C bar squared. And the data that's given might have confusion. So n is the number of molecules and m is the mass of each individual molecule. So nn would be the total mass of the gas, which is the 0.4 kilos. So let's rearrange to get the RMS speed. So C bar is equal to 3 PV divided by, that will be nm, but it's just the total mass. So I'm just going to call it n. So let's put some numbers in. So it's 3 times the pressure, which is 2 times 10 to the 7, times the volume, 0.05, divided by the total mass of the gas, 0.4 kilos. And then let's square root. So the final answer that you should get is 2,739 meters per second. Hopefully that one went okay. Let's try another one. So if you want to pause and have a go at this one, and then I'll take you through the answer. Show that the kinetic theory equation can be written as pressure equals a third rho C bar squared, where rho is the density of the gas. Use this equation to estimate the RMS speed of air molecules at 0 degrees Celsius and 101 kilopascals of pressure, when the density of air is 1.3 kilograms per cubic meter. So let's start with the equation. So PV equals a third nm C bar squared. And remember, nm is the total mass of the gas. So if that's the total mass, then mass divided by volume will be the density. So if we divide by the volume, so that's total mass divided by volume, that would just be the density. So pressure is equal to a third rho C bar squared. So let's rearrange to find the RMS speed. So C bar is equal to 3 times the pressure divided by the density, square root it. So let's put some numbers in. So that'll be 3 times the pressure, 101, times 10 to the 3 pascals, divided by the density, 1.3 kilograms per cubic meter, square root to give the RMS speed. And the RMS speed in this case is 483 meters per second. Hopefully that one went okay. Let's move on. Average molecular kinetic energy. So what I'm going to do now is to combine these two equations and show you an equation for the average molecular kinetic energy that's exceptionally important when doing thermal physics. So obviously these two begin with PV. So it's odds on that we can make these expressions or equations equal to each other. So we can write a third Nm C bar squared equals nRT. And what we're going to do is to do this for 1 mole of a gas, so N would equal 1. And for 1 mole of a gas, the number of atoms N will be equal to Avogadro's number, which is 6.022 times 10 to the 23 from last lesson. So I'm going to get rid of this, and N will be Na for Avogadro's number. So we can write a third, and what I'm going to do is N C bar squared equals RT over N, or Avogadro's number. And if you also remember from last lesson, we said that the molar gas constant, R, 8.31, divided by Avogadro's number, gave us 1.38 times 10 to the minus 23, which is called Boltzmann's constant. So R over Na is equal to K. So essentially we've got a third N C bar squared equals KT. Now on the left hand side that should look familiar. We've got a third N speed squared, which is very close to obviously kinetic energy, half mv squared. So if we times by 3 on both sides, then divide by 2 on both sides, we get rid of the third, and then half, we end up with the kinetic energy. So what we end up with is a half M C bar squared. And on the right hand side, we have to times by 3 divided by 2. So we end up with 3 over 2 KT. So 3 over 2 KT is the average molecular kinetic energy for any individual atom. So the energy is equal to 3 over 2, or 1.5, times K, Boltzmann's constant, times the absolute temperature. So if you got that down, I'm just going to move on. If you need to pause, please do. So the equation, energy, is equal to 3 over 2 KT. So the only thing that kinetic energy depends upon is the absolute temperature. So Boltzmann's constant, K, is equal to 1.38 times 10 to the minus 23. Remember, this is on all data sheets. So I'm just going to give you a quick example question. So let's say the room temperature is 20 degrees. I want you to calculate the average molecular kinetic energy of a single atom or single molecule. So let's pause and have a go at that. So we simply need to use the equation that we've got. So the energy would be 3 over 2, which is 1.5, times K, which is 1.38 times 10 to the minus 23, multiplied by the absolute temperature. So that's 273 plus the 20 degrees, which is 293 Kelvin. And if we calculate that, we get 6.1 times 10 to the minus 21 joules. So no matter what molecule, say you had a molecule of helium and a molecule of uranium-238, the kinetic energy at 293 Kelvin will be identical for each element, each individual atom. However, the difference would obviously be the speed that they travel at, because, you know, same kinetic energy, different masses, consequently different speeds. In the next video, I'm going to do a rather lengthy examination style question where we utilize this equation and we look at calculating the speeds of individual atoms. Just got one more thing to practice before we finish. So how to calculate the mass of a single atom of any given element. So I'm just going to show you this for this lesson, and then in the next lesson we can do some practice. So say for example, carbon-12. So how would I calculate the mass of a single carbon-12 atom? It's pretty straightforward. So carbon-12, all we do is this: we write 12 grams, which is 12 times 10 to the minus 3 in kilograms, divided by, and you just divide by Avogadro's number. So 6.022 times 10 to the power 23. And that would give you the mass of a single atom of carbon-12. So if you want to calculate that now, but that should be 1.99 times 10 to the minus 26 kilos. Very straightforward. And that works for any atom. So if you had helium-4, it would be 4 grams divided by Avogadro's number. So I'm going to give you 2 examples that I want you to just have a go at. And then we'll finish with that. I'm just going to clear this example. Hopefully that's okay. So the next 2 examples are, I want you to have a go at this. So once I've written these out, you can pause. So uranium-238, I want to calculate the mass of a single uranium-238 atom. And Fe56, so iron, an atom of iron. So if you want to pause and do that now. So we've got 238 grams this time. So 238 times 10 to the minus 3 divided by Avogadro's number, 6.022 times 10 to the 23. And that will give us the mass of a single atom of uranium-238, which is 3.95 times 10 to the minus 25 kilos. And then one more, the iron, so it's 56 grams, so 56 times 10 to the minus 3, again divided by Avogadro's number, so 6.022 times 10 to the 23, and that will give us the mass of a single atom of Fe56, so that would be 9.30 times 10 to the power minus 26 kilograms. Bit of a lengthy lesson, quite a lot of information in that one, but I hope you found it useful. So thanks for watching, and I will see you at the next one.